Hey guys, how are you? I'm here today to talk about ZPowder again, today with audio, because I want to explain what I did and explain a little bit about ZPowder. ZPowder is a personal project of mine that I have been working for the last months, and it's basically a automata simulation for the Dust game. If you guys have ever played that web browser-based Dust game, which simulates powders or powder game, there are several names, several implementations. Basically, the thing is a simulator that simulates some basic rules for automatas that create visual representations of water, sand, oils, anything that you can simulate with cellular automata. And what I did today, I implemented a generic automata particle type, which can run some rule sets that makes the particle type able to simulate more traditional cellular automatas like John Conway's Game of Life. So let me show it to you. What I did for I implemented a new particle updater. My system uses particle updaters to register updaters on startup. So it is able to update each particle type using its respective updater. It was a little bit hard to implement generic cellular automatas because they sometimes require you to update particles that have no type. Like how to explain this? For example, John Conway has a rule when a particle is empty and has three neighbors. So let's represent here. So if this is the particle I'm checking, and it has three neighbors that are from the automata type, from life type in my grid, this particle must become alive. But my system automatically ignores this particle because it's an air particle. It's not a particle it thinks it should update. So what I did is when you have a life particle here, an automata particle here, either of those, they check their neighborhood and apply their rules to their neighbors also. So this makes it work. There are a lot of optimizations so that we don't cross double check, triple check particles that have already been updated. And I thought this worked really well for me. At least performance issues are related. The performance issues I currently have are related to other stuff. This is quite performant for what I thought it would be. So let's get to it. I'm talking too fast. So my new updater, my new particle updater, this is what I did. It is a rule set based updater for cellular automata simulation. And what I did was to create a rule set which is based on the number of neighbors and what happens when a cell has that number of neighbors. So for Conway's Game of Life, what I did was to use the Conway rule, which is when a cell has two neighbors of the same type of there's only one type in Conway, but my system has a lot. So when a cell has two systems of the same type, it is kept, it doesn't die. And when the cell has three neighbors, like this one, if those three are from are live cells, this becomes alive or is kept, either one. So this is the create rule here. And any other combinations, any other number of neighbors results in the cell dying. So if a cell is alive and has four neighbors, it dies. It becomes air, which is the fallback rule. So let me show you what this means. What happens? I'm using a really big resolution here. My engine usually runs in a smaller resolution, but I think this is prettier and nicer to record. So let's do this. So when this is send, sorry. So this is my engine actually. It simulates particles using the Dust Game Cellular Automata rules. It is really optimized to run multi-threaded using everything I can to make it really fast. It uses checkered updates like what's the name of the game? Noita uses. I have implemented everything for rendering the GPU. I don't pass everything to the GPU. This is running on the CPU, by the way, This is not a compute shader. This is running completely on the CPU. I have several types of particles. I have fire, water. I don't remember the keys exactly for them. This is steam, I believe. C clears. I have lasers. I have gunpowder, which ignites. I have gasoline, which also ignites. I have oil, which also ignites, but slowly. Let me see. This is gasoline. I have. Oh, this is the entire. This is copper. Copper is conductive, so if I find the lightning bottom, energy, I have energy somewhere. Oh shit. So yeah, spoiler there. Let me change the automata implementation. So let's see the automata implementation. If you want to see more about this engine, more about the powders that I have implemented already, you can go to my YouTube channel. I have videos there, although with no commentary, but I intend to create videos with commentary from now on, so I can explain what I'm doing. People said to me, "Explain what you're doing. Don't just put a video online without audio and hope that people will understand what is happening. Even if it's beautiful or interesting, it won't be as interesting if as a video where you explain." So I'm trying to do that, but I'm not good yet with preparing videos. So let's do this. Let's change. I'm going to start the presentation with the Conway updater. I'm not yet able to change this in runtime because all updaters are not particle types. The particle type is automata. This is like a sub-particle type because this is the particle updater. The types are like laser, oil, because they share updaters. Like oil shares the liquid updater with water, so I have to implement the same thing. And the automata should share updaters, but I don't want to create like 10 types of automata since they are like the same type. This is more of a subtype, so I intend to implement subtype particle updating in the future. I know how to do this for automata already. I think I'm going to use one of the particle data that is intended for something else to check its type, because automata particles don't use like velocity, so I can use the velocity data to store the subtype, and I have a lot of subtypes there. And I don't have to increase my memory bandwidth for usage. So this is what I think I'm gonna do. I'm not sure yet, because I wanted to have different colors also for different subparticles, which makes it a little bit harder. Uh, okay, so let's do this. The first one I want to present to you is Corner Game of Life, because it's one everyone is familiar with, and it's also uh, it's a good way to show that this is actually working with this update scheme that I did, and it's easy to recognize because people usually know what Conway is. So there you go. Sorry. This is the implementation of Conway's Game of Life in my engine. As you can see, even with this resolution, Conway is performant. It's it is very performant actually, but my engine is doing a lot more than this behind the scenes, which makes it a little bit hard to make it performant. But this is quite performant right now. It interacts with my other particle types as expected. You can throw sand at it. Oh, there's diffusion. I didn't mention that. Fire destroys life particles. Any automata particles are destroyed by fire, so you can have some fun. And what is interesting about this is that since this is running on my engine, I can do other sets of rules, not only related to the same particle types. Ah, look, a little critter. This makes it really interesting for me because particles, automata particles that I have implemented this way, they don't need to use only themselves to for their rules. They can generate other kinds of particles. For example, I have created. Let's go to the updaters, type it. Sorry, not this. I want particle definitions, and here cellular automata. So like the Banzu, I named this one Banzu. This one I wanted to do something that was really eager to grow and really resilient to fire. So what I did was to change a little bit the rule set. So when a particle has one neighbor, it's kept. This makes them really resilient to death. When a particle has two neighbors, it is created. So new particles, like if this particle is empty and it has two living neighbors, two automata neighbors, this becomes also an automata neighbor. Having a lower number for neighborhood here makes it makes it grow really fast. And then I made that when when a particle has three neighbors of the same type, then it becomes water. This is really interesting because this makes a really beautiful result. Let me show you. So here, uh, come on Unity, come on, you can do this. Here, so let's clear the screen. When you create, it starts to grow, and as soon as it reaches three neighbors, it becomes water. And as you can see, even if I delete it, it it just don't want to die. And eventually, I think the water is going to slow it down, and everything's going to become water, infected water, something like this down here. I was calling this infected water. It's really cool. I really enjoy the visuals. This one is a little bit heavier. I haven't yet implemented a dirty checker for this, which means whenever there is a automata particle, the entire chunk is always updated. This is why the frame drops a little bit. Let's see. Yeah, a lot actually. But this should be straightforward to implement. The only issue that I had with this so far is that you have to be able to detect stable arrangements, like when a particle is in a stable arrangement that is always changing but always resulting in the same structure, like in one frame it occupies these three slots, and then in the next this three, and then in the next this three again, like John Conway tends to do. This is an oscillator. It's kind of hard because this causes updates always. What I did to solve this is to add lifetime to these particles. This is a really cheap way of dealing with this because they die after a while, so it doesn't matter. But as you can see, if you fill the screen with oscillators, then you have an entire screen updating, which is really bad for the system because when you update some particles, you update the chunk. Even though the chunks are small and this is really fast, as you can see for the Bonzu particle, the Bonzu is really heavy because it generates water, it keeps changing, keeps growing, occupies the entire screen really fast. But still, for me, this is really interesting. So let's change, let's try another. Let's try, I'll leave the secret for the last because that's my favorite. I forgot the other types. I already showed this one. This is gonna be less. So Charnel. Let's select Charnel. Charnel was the opposite from Bonzu. I wanted something. Oh, sorry. I wanted something more active, more uh, ever changing, smaller. So what I did was, let's see. I added. I set up so that when the particles have two neighbors, they create new automata particles. This is important because one neighbor is too little, and keeping one neighbor results in growing really fast. So keeping two and creating on two grows a little bit slower. 3 and 4, the particle are kept. The particle is kept. This is so the particle can have a little bit of lifetime on the screen. And 5, the particle becomes fire. And what this actually made what this behavior actually represents is particles that move fast and leave a fire trail behind. This is really interesting because when the particle is kept alive in 3 or 4, it is really probable that a new particle will be created because of the two, either on one side or the other of the thing that is being created. And when that happens, the one that is 3 or 4 can easily become 5 and become fire, which will kill the particles and make the particles move on the screen. So uh, sand again. So look, this is what happens. It creates little critters that send fire behind them. It's really interesting. I really like this. Even critters that don't send fire. This is really nice. I really like this one, and it's way more optimized now, and it creates this amazing effect. Yeah, actually, because this is fire, this is why the particles are going only down to the sides, because the fire is killing everything above it. But it's really cool, man. I cannot get tired of watching this. I really like this. I don't know what to do with this engine yet. I just did it to play, to see if I could program by myself something like Noita, something like the developers did. I watched a video on YouTube about how they did it, how they got it to be so performant. Because I have actually watched another video that was about the Dust game, this part of the simulation, and I implemented it. And I really disliked the implementation that the guy did in the video, so I decided to do it myself to see what I could do. And I really enjoyed doing it, but my performance was really bad. This is how I got to Noita's video and to implementing a system that was really faster. And now for my favorite part, for the best automata, for the most amazing graphics, the circuit updater. The circuit updater, I did it by accident, and I really enjoyed it. It results in amazing visuals. For some reason it grows, but it leaves gaps between cells, and it's really beautiful because of the lifetime, which makes it expand and die and expand again and expand on the depth, and it's crazy, and it's really crazy. I'm going even to lower a bit the resolution so the performance is amazing, so you guys can rejoice as I did when I saw this for the first time. So let me explain the rule set again. The rule set for this one is like what I'm saying. When the cell has two neighbors, so if this cell is empty and has two neighbors, this cell becomes an automata. When it has three neighbors, it is kept, and when it has four neighbors, it is also kept. So this keeps a lot of cells. But what happens is that when a cell has five neighbors, it dies. 6, 7, or 8 also. The maximum neighbors a cell can have is 8 because it has only 8 neighbors. But when the cell has 5 neighbors, which means if these 4 are alive and this is alive and any of those are alive, it dies. So it leaves a gap. So if any neighbor closes half of a circle, it creates a gap. So this results in what you're about to see. Ah, I forgot to change the updater. Sorry. No, I didn't. Let's do this. Ah, sand again. Enjoy. Oh man, I like this so much. Let me shut up so you guys can enjoy. I call this the circuit updater, obviously, because of the little circuit paths it creates. And these waves are the lifetime waves because the particles are created where I started and then they die, and then the particles created from them start dying, and it creates this wave. It's really nice. This resolution is actually really ugly because the pixels are not aligned. So let me go back to 5, which is a half. I really enjoyed this one. Again! Look at this. It grows really fast. And then it starts growing forever. don't go away yet because I'm about to queue a lot of them. So you will see another effect that's really interesting because of the lifetime. This right now is really heavy, probably more less than 10 FPS. No, 12 FPS, which is really good. I was with about 1 FPS before. And there are several things that I discovered. Like sometimes the cells create this straight line pattern. I haven't found vertical ones yet. I don't know why this pattern only happens in a horizontal. Probably has to do with the way the stagger updates occur with the threads in the CPU, or maybe because of the region boundaries and the reaction updaters that use grid to reduce the amount of updates that I have to do. But man, this is really cool. Look at this. I bet you never seen someone so excited about something so stupid. Look at this. It looks like there's energy going through something like that. The region where the cells are dying is really active and it's really interesting. This I think this problem happens this flickering because the cell has two neighbors and it shifts to the side and then happens again. But as you can see, the secret overcomes this as the time goes on because the cells die. I love this pattern. I loved it. So, and it's really resilient. As you can see, I'm drawing on the screen and watch what happens when the cells start dying again. Look at this. Because when I kill them, the new ones occupy their space, and now they're going to start dying and becoming alive from the drawing that I did. You can clearly see my drawing lines here. By the way, this is based on online drawing, so this is why even with the frames so low, the lines are straight and complete. Look, you can see the smile in my face. This is my face right now, smiling. And I can even try to play with fire here. Look at the fire. This is so cool. There's only one interaction so far between automata particle types and other particle types like fire. Like fire? What I'm saying. There is only fire interaction with the automata cellular type for now. But I'm thinking on how to make it more interactive. I cannot speak when I'm looking at this. This breaks my brain so hard. Oh my god. Jesus. Well, let me end this here. This is it, guys. This is what I did today. I'm really happy about this. I have been working this for several months now. I work on a games company, so this is not my main work. I just set aside a few hours every month to add a little bit to this. Uh, that's it. Thanks for watching. Oh, also, sorry, if any of you guys want me to maybe talk about the code behind this or about the logic, give an in-depth explanation, talk about threading, talk about memory management, this is an awesome project to discuss these topics because this uses everything. This has to run really fast. There's a shitload of particles to update, and this is all running on the CPU, so you have to be really careful on the amount of checks you do per particle every frame. And this is also trying to run on zero locations and using a data-oriented scheme, not using jobs nor burst. This was all done by hand using threads directly. I did my own memory management, not real memory management, but like Unity memory management. You guys know. So if you guys want, I can make a sort of a tutorial lesson video about this. Uh, just send the request in the comments down below. Also remember to like and subscribe. That's it. Go.